the phase line diagram is for a system two-dimensional differential equation, or two differential equations. It's called the phase plane. In more general systems of differential equations, it's known as the phase space of the system of differential equations. So next we have a definition. We say that an equilibrium point of the differential equation star is either, or we'll say not either, but we'll say it is stable or a stable equilibrium point if the following is true, provided that for all epsilon greater than 0, there exists a delta greater than 0 such that if the distance between y1 and y0 is less than delta, then the solution phi of t, and this is where I am going to say, with initial condition y1. So this is the solution to the differential equation star for the initial condition y1. So this solution exists for all t in the interval from 0 to infinity. And if your initial condition doesn't start at 0, you can change this, rewrite it so that it does start at 0. But the main condition here is that the solution has to exist. And the main thing here is that the distance between the solution with initial condition y1 and our equilibrium point has to stay less than epsilon for t greater than 0, greater than or equal to 0. So this is the exact correct mathematical definition of what a stable equilibrium point means. It says that as long as for any reason, for any distance that you want to take close to y0, so for any initial condition y1 that's close to y0, and for any tolerance, epsilon tolerance, if the distance between y1 and y0 is less than a small enough value, there has to exist a small enough value, or an initial condition that's close enough to the point y0 that the solution stays within epsilon of that value y0. So this is what a stable equilibrium point is, what it satisfies. And furthermore, it's important to point out here that stable here does not mean that it approaches the equilibrium point. It just means that for any tolerance epsilon, for initial conditions that start close enough within delta of the equilibrium point, the solution itself, starting at that initial condition y1, will stay within epsilon of the equilibrium point. So within that tolerance of the equilibrium point. So I'll give you a good picture of what this means. And this is a 2D picture, and I'll extend our idea to 2D. This is saying that if you have an equilibrium point y0, then for any epsilon, so for no matter how close you want to get to y0, there's always going to exist a smaller delta, region around y naught, such that if solutions have an initial condition inside this delta region, the solution will stay within epsilon for time t greater than or equal to 0. The solution might go outside of the delta ball, but it has to stay within the epsilon ball of the differential equation. And this is the solution phi of t comma y1. So no matter what, for any value of epsilon, no matter how small you want to get, there always will exist this space, this delta region, and that's what this is saying. So it's important to point out that this is not saying that the limit, right, the limit of the solution does not have to equal the value y naught. This is actually a different type of stability, which is a more strict type of stability called asymptotically stable. So an equilibrium point is asymptotically stable, provided that it is stable. So it's a stable equilibrium point, and there is some delta naught, positive delta naught, such that if the distance between y1 and y naught is less than delta naught, then the limit as t goes to infinity of the solution, v of t y1, is equal to y naught. And this is a stronger condition than just stability. This is saying that not only is the solution staying close to y naught, to a given equilibrium point, but furthermore, its limit in the limit as t goes to infinity, it's asymptotically approaching the value of that equilibrium point. So this is a very, very important distinction. But what this is saying is that for an asymptotically stable equilibrium point, there will always be a maximum region where it's essentially saying that if you start close to the equilibrium point, you'll end up going to that equilibrium point. You'll in the limit, the solution will evolve to be that equilibrium point. And the last thing that an equilibrium point could be is unstable. So an equilibrium point is unstable if it is not stable. And you can go through and take the logical negation of this statement right here to get the explicit definition of unstable. This is a good exercise to go through and do, but essentially it means that the solution, no matter what, that will be moving away from that equilibrium point. So in the examples that we've seen so far, the Malthus non-dimensionalized differential equation, y prime equals y as an unstable equilibrium point at y equals 0, and the Verhelst non-dimensionalized differential equation has an unstable equilibrium point at y equals 0 and a stable equilibrium point at y equals 1. This is actually an asymptotically stable. So asymptotically stable equilibrium point at y equals 1. And it's always helpful to visualize these concepts if possible. And it's definitely possible to get a nice visualization of this if we go through and do a plot of the solution. And I'm going to focus on the Verhelst differential equation, but this applies anytime you can do this anytime you have a form for the solution. So the idea here is that I've drawn an epsilon region around both of these equilibrium values, so y equals 0 and y equals 1 right here. This is an epsilon region around both of these. It's the green region, or the region between the dotted lines here, and the region between the dashed lines here. As this region shrinks, the region gets smaller and smaller and smaller. But you can see that if we start with our solution at with the initial condition of 0, with an initial condition of right here of 0. So our solution is right here at this point. This is our initial condition. We consider initial conditions that are close and around our solution. And right now, this is within a distance epsilon of 0. You see that all of these solutions, as time goes forward, move away from 0 as time advances. So no matter what, any solution with an initial condition inside any epsilon region, no matter how small epsilon is, and no matter how close we choose to get, to our equilibrium value of 0, even if we choose to get a little bit closer, let's say we look at an initial condition that's smaller, that's closer here. We take a smaller region to look at our solutions. Like right here. All right, for any collection of solutions that we look for with an initial condition in this region, this is going to eventually escape the epsilon region for y naught. And not only that, it's going to head towards, as time advances, So as our time advances, our solution is going to head towards this right here. That's going to head towards the epsilon region, and we'll make this a little bit larger here. And enter, all of those solutions will enter in to the epsilon region surrounding the second critical point. So I think this is a pretty illustrative demonstration of what we mean by an unstable versus a stable critical point, or critical value here. And specifically, this is, 1 here is an asymptotically stable critical value for this function. So this is going to be a big idea, and extending this is going to be one of the big things that we're going to do a little bit later on. Another idea that we're going to extend from 1D to multiple dimensions is going to be the idea of a potential function or potential energy function. Very often, if we can express our function f in a simplified manner using a potential function, we'll be able to say and determine properties of the behavior of the system. So we call some function phi of y a potential function and it's called a potential function because it's related to the idea of potential energy in physics. We'll see it's more general than that and applies to more general scenarios, but it's very, very, very intimately related with the potential energy function in physics. Phi of y is called a potential function for the differential equation if f of y can be written as negative phi prime of y. You want to note that this is saying that f is negative the y derivative of phi. Phi is a one variable function of y, and the derivative of it is with respect to y. So that's important to even write down. And if this is the case, we can actually prove a number of different things very, very nicely about properties of the general solution to our differential equation. If phi is a potential energy function or a potential function for a star, then the composition phi of y of t is a strictly decreasing function of t along any non-constant solution y. Second thing that we can show is that y naught is an equilibrium point of the differential equation if and only if this is sometimes abbreviated as IFF in mathematics texts. The derivative of phi at y naught is equal to 0. So if and only if is important that you realize whenever you see if and only if, it goes both ways. So this is saying that y naught, if y naught is an equilibrium point, then the derivative of phi at y naught equals 0, and vice versa. If the derivative of phi at y naught is equal to 0, then y naught must be an equilibrium point. Okay, so this is if and only if statements are very, very important to distinguish from just if statements in mathematics, or if-then statements. And 3, if y naught is an isolated equilibrium point, then we also have to include something as well. So if y naught is an isolated equilibrium point and phi has a local minimum, at y naught, then y naught is asymptotically stable. And we'll go through and we'll prove the first two of these statements. Three is the proof for it is in the book. And I recommend reading through it, but it's something a little bit long to go over right now in the lecture. It's worthwhile going through and understanding it. Proof of 3 is a proof by contradiction. But we'll go through right now and just do 1 and 2. So for 1, we can go through and directly do this using the chain rule. Take the derivative of phi of y of t. And it's interesting to ask yourself why we can apply the chain rule here based on our previous differentiability assumptions. Be very, very careful about this. Why can we do this with phi? But according to our previous assumptions for the solution to y of t, we can go through and do this. This is going to be phi prime, the derivative of phi with respect to y times y prime, And based on the definition of phi prime, this is the same thing as f, negative f of y of t. And we also have that y satisfies the differential equation, so because y prime satisfies the differential equation, y prime is also equal to f of y, which is f of y of t. This is negative f of y of t squared. And f of y of t squared is always positive, which means this is always negative, which proves what we want to prove, because this is showing that the derivative of phi of y of t is a decreasing function. Its first derivative of this composition is always negative. So phi of y of t is strictly decreasing. With respect to t. And part 2 is also relatively straightforward to go through and prove. It's really just to call it into the definition, that a critical point or an equilibrium point, y naught is an equilibrium point if f of y naught equals 0, but by definition, f phi prime of y naught is equal to f of y naught. So this must also be equal to 0. And like I said, part 3 is a proof by contradiction. And is a little bit longer, so we're not going to go over that proof right now. But if you're interested in it, it's in chapter 1 of the Kelly book.